So remember yesterday I told you guys how these couple sections are going to be really rich in vocabulary. Okay, so today the first new thing that we're learning about is called the circumcenter. And that's the point of concurrency. Remember, that's the center of gravity of the three perpendicular bisectors. Okay, so you can tell that they're perpendicular bisectors because perpendicular for the right angle, bisector because each half is marked as congruent for each one of these. So this is called the circumcenter. So this line, which we called X, is the perpendicular bisector for the side BC. Your line Y is a perpendicular bisector for AB, and Z is the perpendicular bisector for AC. Okay, so circumcenter is our new one. So yesterday we talked about the orthocenter, which is where what meets? The altitudes. Okay, and where all of the medians meet is called the what? Centroid. So centroid, medians, altitudes, orthocenter, perpendicular bisectors, circumcenter. Okay, so those are definitely things that you're going to want to make sure that you look at. So for the circumcenter, we have a special theorem, which is what we're going to talk about next. So it tells you that the circumcenter of a triangle is equidistant from the vertices of the triangle. Okay, so the circumcenter is equidistant from the vertices. So equidistant is something we have talked about before. We just break it down. Equal, distant, distant. So it's equidistant from both of the vertices. So if I look at my picture here, point P in the center, that is my circumcenter there. That means it is going to be equal distance from the vertices, which, Ziggy, what are our vertices of this triangle? What are the vertices?
The vertices are A, B, and C.
Yep, so from A to the circumcenter, that's going to be the same as from B to the circumcenter. That will be the same as C to the circumcenter. All right, so for this triangle, remember that point P is the circumcenter. Okay, this means that all of these segments are going to be equal in length. So from A to P, that length is equal to B to P, and that would be equal to CP. Right, so another way that you can think about this is it's the same distance from each vertex to the circumcenter. Okay, so same distance from each vertex to the circumcenter. Yesterday when we did the orthocenter, we found out there were multiple places where the orthocenter can be. This is going to be similar to that of the circumcenter. So the circumcenter can be inside, outside, or on the triangle. Okay, so that's very similar to the orthocenter. Now, if we look at the different cases, bless you, you can see it is extremely similar because just like we investigated yesterday, if it was an acute triangle, it was inside. The same thing happens with the circumcenter. If it was obtuse, the circumcenter is outside. And if it is a right triangle, then it is on the triangle. Okay, so something else special about the circumcenter is that it would be the center of its circumscribed circle. And we'll talk about what that means. So the circumcenter of a triangle, ABC, is going to be the center of its circumscribed circle. So if you look at the picture, that'll help you with that definition. But one thing that you should notice is with the triangle, all of its vertices are on the circle. Okay, so if it's circumscribed, you can see that the circle goes around the triangle. The triangle is inside it with its vertices on the edges. And so this is going to be a circle that contains all three vertices of the triangle. Okay, so like we said here, all three vertices are contained on the circle. Okay, and then P is the center of the circle. And therefore is the circumcenter of triangle ABC. So this is just another way to show you what the circumcenter is. If you look at some of our pictures above, you could see that we had to have all those marks. We had to have the perpendicular bisectors. But if we know that it's a triangle where all of its vertices are on the circle, then we know that this is a circumcenter, which means you know that all of these lengths from A to P, from B to P, and from P to C are congruent, because that's what the circumcenter tells you. Okay, the circumcenter is going to be equidistant from each of those vertices. All right, let's flip it over. So in our first example, you are told that DG, EG, and FG are all perpendicular bisectors of the triangle. What you have to find is GC. So sometimes what I like to do is I just like to highlight what I'm trying to find. That way if I'm marking stuff off in my circle, that might be able to help me. Okay, so we know that they're perpendicular bisectors. If these are perpendicular bisectors, that means the place where they meet is the what? The circumcenter. Okay, so from there, since G is the circumcenter, of the triangle ABC, let's think about what we know. So we just talked about the circumcenter theorem, where any distance from the circumcenter to a vertex is going to be congruent. So that means AG, BG, and GC, all of those are congruent. Really, the one I'm going to focus on is what? GC is congruent to? Yeah, and Julie, why would we want to focus on that one?
Because that has like its measure already given.
Right, so BG we have a measure for. So we do know that BG is equal to CG. Okay, again, it's also equal to AG, it's just AG isn't particularly helpful for this. So we know BG is equal to CG. This would be by the circumcenter theorem. Which tells us there's an equal distance from, we'll say, vertices to circumcenter. Okay, so since G is the circumcenter of triangle ABC, we know that BG is equal to CG by the circumcenter theorem, which tells us there's equal distance from vertices to the circumcenter. So that means that we're trying to find GC, which same thing, right? CG, GC. That means GC is going to equal the same length, which is 13.4. Okay, now if you look at this diagram, can you see how maybe this 7.3 is trying to trick you? Okay, so remember that it goes from the circumcenter to the vertex. What would point E be? What would it be? Yeah, it'd be the midpoint. And then, CJ, we're going to ask me something?
Yeah, I was gonna ask you, I was gonna say, so, like, the one we learned yesterday,
Yes.
this has to be 1/3 shouldn't AG be 13.4?
So what we learned yesterday is with your centroid. And so because this is not your centroid, the 2/3 won't apply.
Okay.
And that's a good question because they do look really similar, right? So your centroid is when all of your medians are going to meet. And what is the only difference between the medians and the perpendicular bisectors?
Perpendiculars, bisectors, straight in
That the median does that too. It's they're not, yeah, it's that they're not perpendicular, right? It's kind of like both of them put together. So yesterday we learned about the medians, and the medians go to the midpoint. So that's how I would try to remember it. Medians go to the midpoint. We learned about the altitudes, and the altitudes are perpendicular, right? The height, you're going to see that right angle. The perpendicular bisectors are both of those put together. And that's a good question because they do look very similar. And obviously when you have a test or a quiz, you'll be dealing with all of those. So you'll have to be able to differentiate. Yeah, Rachel. Yes, yes. So if this is 90 degrees, then yep, this is 90 degrees. Yep, and you're right, because that is the midpoint. Each of those are congruent. Now we don't know what their lengths are, but they are congruent to each other. Same thing here. So both of these are congruent, and then both of these are congruent. Now, notice that those aren't marked in the diagram. Sometimes they are going to be. The only reason we know that that's the midpoint is because the example tells us. So because it says it's the perpendicular bisector, that's how I know. Yes.
So if it did show that the sides were like congruent,
Mm-hmm.
would that be like an easy way of us like knowing that it's this theorem?
Yes. So you would know it's this because you're looking for both parts of that side to be congruent and the perpendicular bisector. So it'll have those two in one. All right, now for our next example, still talking about the circumcenter, we are going to find the circumcenter of this triangle, and they give us vertices that we are going to plot. So go ahead and plot those 3 points. while you guys are doing that, I will get you guys some straight edges so that those look nice.
How would they do the graph?
Oh, we're gonna change those. We're gonna, you can change the scale.
Oh, sorry.
Pass them to the left.
Should they make each line 6.2?
Yeah, good eye. So if you look here, you can make each one 2, or if you want, you can extend it as well. So if you'd rather just extend it up a little bit, you can. You see that your graph goes to 5. If you just want to extend that up a little, you can, or you can go by 2s. So, like I said, whichever way you want, you can do that. I did change mine so that this was 4 and that this was 8. So 2, 4, 6, 8. And then I had to make sure that this went out to 10. So no matter what, you're going to have to change your x's. So 4, 8, 10, negative 10. Just going to label that as negative 2, negative 4, negative 8, negative 10. So H was right at 0, 0. My next point, and I am going to label these, so I want you to do that too. And then J was at 10, 0. And then I have 0, 6. So this was my triangle. And then we're just going to label our vertices. So H was right at the origin. J is my x-intercept. K is my y-intercept. Okay, so if I'm going to find the circumcenter, I have to do a couple of different things. So it's a perpendicular bisector. We actually did this in 5.1. So when you find your perpendicular bisector, to get the bisector part, what point do I want to find here? The midpoint, right? So I'm going to find the midpoint first, and I'm going to find the midpoints of HK. And HJ. Now, we talked about earlier, if it was a right triangle, where is my circumcenter going to be? It should be on the triangle, so just keep that in mind. I'm going to give you your formula for your midpoint. I think it's a good reminder. X1 plus X2 divided by 2. But for this one, these are actually very easily found because you're on your x-axis. So from 0 to 10, where's your midpoint going to be? At 5 what? 0. Okay, so your midpoint of HJ is going to be 5, 0. So I'm going to go ahead and plot that. So if this is 4, 5 is halfway in between. Okay, and then we're going to do your midpoint of HK. So again, if this is from 0 to 6, halfway in between is going to be 3. So this would be 0, 3. You could also use the coordinates. And then to create the perpendicular part, all you have to do is create that 90-degree angle. And then so step 2, we're actually just going to write it out. So you're going to draw the perpendicular bisector. Through your midpoints. Now you could also find the midpoint of KJ. We are going to do that to see how nice our prediction went. That one turned out pretty good. So you're trying to draw it so that it's perpendicular. I can see mine's going to be a little bit off here. Right? And then it should intersect right on your side. I'm sorry, that's a little hard to see. Okay, and then you're going to find your intersection, and that is your circumcenter. Now this one is special because it is a right triangle. So if I were to find the midpoint of KJ, right? If I find the midpoint of KJ here, I would have 10 plus 0 divided by 2, 0 plus 6 divided by 2. What would my midpoint be? It would be 5, 3. It would be the same as your circumcenter. Okay, so your circumcenter here is over 5 up 3. We're going to make a little note. Okay, so this is also the midpoint of KJ. Okay, so again, when you have your right triangle, you only need to find the perpendicular bisector of your two sides. So you only need to find the perpendicular bisector of two sides. For a right triangle. And that's because they should always intersect on the triangle. And when they intersect on the triangle, they're going to intersect on the midpoint of that side. Now, why did I choose to do HJ and HK instead of finding JK at the beginning? Because really, I mean, you could find the midpoint of that. Yeah, Colin?
Just because it's not like I'm HK, you can like see how far it is apart.
Yeah, on HK, I can just count using the units, can I? Can I see how many units they are? Whereas if it's slanted and going through multiple boxes, I can't just estimate it right away. I'd have to do some kind of calculation. But if I have it on the axis, it's just going to be really quick. Okay, so that's how we did it like that. All right, so the next thing we're going to talk about is something called the incenter. So a triangle has 3 angles, which means it has how many angle bisectors? 3. A bisector for each angle. The point of concurrency, or the center of gravity for the 3 angle bisectors, is called the incenter. So in our drawing, here is our incenter. Okay, and the incenter is formed from the angle bisectors. So if we look at our lines here, I would say line X is the angle bisector of which angle? A. And then line Y is the angle bisector. So go ahead and just fill in that last part. I'm just saying of, and then I want you to say what it is. And then line Z okay, now when you're looking at the drawing, you can tell that this is going to be a bisector because both of those angles are marked the same. If you look at Y, line Y is cutting angle B in half. And I can tell these are the same because they have those 2 marks. And then the last one has my 3 marks. And Z is the bisector of angle C. Now the incenter is like the centroid. The incenter is always inside the triangle. So it doesn't matter if it's acute, obtuse, or right. The incenter is always going to be inside the triangle. And then you just have examples here. So if it's acute, it's inside. If it's obtuse, it's inside. And then if it is right, it is inside. Yes, Julie.
Can I ask a question about like this at the top of the page?
Okay.
For like in this one triangle that shows, the triangles that have like every opposite triangle, are they all congruent? Like do they make congruent triangles inside?
Well, we have the 2 sides. We would just have to prove that these angles were congruent, and then we could prove it by SAS. And if we could find a way to do that, then yes, they would be. There's no way to know, like we don't know if this is an angle bisector, so we can't say for sure that they are. We know that this angle is congruent to this angle by vertical angles. We know that this angle is congruent to this by vertical angles. We would just have to know that it cuts those in half. And we don't. But that is a good thought. Alright, and then we have an incenter theorem that is similar to our circumcenter theorem. So the incenter theorem tells us that the incenter is equidistant from the sides of the triangle. Okay, so equidistant from the sides. If you recall with the circumcenter, it was not equidistant from the sides, it was equidistant from what? Nope, the vertices. Yep, equidistant from the vertices. So to each vertex, this is going to be equidistant to each side. So let's go ahead and label. So here, P is our incenter. Oh, and to this, we're just going to add. This is when the lines are perpendicular. Okay, so when the lines are perpendicular, that's the part that's equidistant. Okay, so not just any line, it has to be the ones that are perpendicular. So P is the incenter of triangle ABC. And then we're just going to highlight here what would be congruent. So before we talked about how it would go to the vertex, but not this time. This time it is going to go to each side. So P to X, P to Z, and then P to Y are going to be congruent. So the way that you can pick those out is going to be based on that right angle there. Okay, and then you do have angle P in the center. So we would know that P to X is the same length as P to Y. That's the same length as P to Z. So the distance from the incenter to each side is equal when the segment to the side is perpendicular. Okay, so the distance from the incenter to each side is equal when the segment to the side is perpendicular. Now, we just talked about a circumscribed circle. Now we are going to talk about an inscribed circle. So the incenter is going to be the center of the triangle's inscribed circle. And if you look at this picture here, you can see how they're different. Anybody want to tell me? Yeah, Griffin?
The circle is touching the midpoint of each segment.
And the circle is, what's the difference between this one and the last one?
It's inside
That, so what's inside? Just be specific.
the circle.
Okay, so the circle is inside the
Triangle.
triangle, whereas before it was what?
Outside.
Okay, so this time it's the circle is inside the triangle as opposed to the triangle being inside the circle. So that's how those are just switched around. And this doesn't necessarily touch the midpoint. If you even kind of look at this side here, you can see that that's not going to be halfway, but there is a point of the circle on each part of the triangle. It just isn't necessarily your midpoint. So P is the incenter of triangle ABC. Since P is the center of the inscribed circle. So what that would mean is, because it's the incenter, you would have these equal distance segments would be perpendicular to each side. Oh, and I think A got cut off on that. So that is triangle ABC. All right, and then for our next example, they tell you that MP and LP are angle bisectors. So they're telling you that they're angle bisectors as opposed to showing you with particular marks. So these are going to be your angle bisectors of the triangle, and then we have to find each measure. Okay, so MP and LP are angle bisectors. Find each measure. So the first thing we're going to do is we're going to find the distance from P to MN. Okay, so from P to MN. What we know is that P is the incenter of triangle LMN. So remember, the incenter is where the angle bisectors meet. So I'm going to say, and therefore, P is equidistant. I put equidistance, but it's really equidistant. So it's equidistant from P to, and it's really equidistant from P to all of the sides. So from P to ML, and P to MN, as long as that distance is 90 degrees. So the distance from P to this side ML is defined here as PQ. Now, even though we don't have a segment in our triangle, that doesn't mean that it's not the same distance. If we wanted to, we could draw that segment in, but we don't even have to. Okay, since we know that PQ is equal to 5, really you don't need that symbol for the length. The distance from P to MN is also 5. So again, like I said, you don't have to draw that in. If you wanted to, you could, right? This would be your perpendicular segment, and if this is 5, then this would be 5 as well. Okay? It doesn't have to be labeled on there for you to find that length. We're also asked to find in part B the angle PMN. So I'm going to draw that angle. Use a different color. Okay, so if I go from P to M to N, I'm trying to find this angle here. I'm just going to put my arrow on that. Okay, and so really what you're trying to find is this angle. we were told above that LP is the angle bisector. And if I look at LP, I can see that it's going to be bisecting angle MLN. So let's go ahead and find that measure. So if you look at your picture, if you know that this is an angle bisector, and this is marked off as 50, what do I know about this side? It's 50, so altogether it would be 100. Now, I'm trying to find this angle here. What I'm going to do is I'm going to look at this triangle as a whole. So I like to draw like rough sketches so I can visualize this. So I just found out that this angle was 100. I already know angle N is what? 20. Right? So the measure of M plus L plus N has to be 180 degrees. Well, I already know that L is 100 and N is 20, which means angle M has to be what? 60. Right? If I subtract 120 from both sides. Now, remember, they're not just asking you for M. This is the bisector. Because PM is the bisector, I'll call it MP, bisects angle M. So that means the angle that we're trying to find, the measure of PMN, is going to be half of angle M. So half of 60, which means it's going to be 30 degrees. I am going to have you guys write your homework down for this section.